Thanks, everyone. Thanks for coming to our session. I'm Yan, and this is my colleague Shubo. Both of us are part of the engineering team at Conviva. Today, we are going to talk about our experience in building a near real-time and long-running Spark application with high scalability, high stability, and high resilience. So we are going to go through the details of a few techniques that are used by us for building a high-performing and low-cost Spark application, from how to monitor the long-running Spark application to how to optimize the Spark performance through several software-level optimization, and how to handle node failures such as driver and master failure, which can be tricky if your application relies on a huge amount of historical data and you're required to recover the state with minimum latency. So all of these techniques will be around a specific Spark application built at Conviva. It's called Video AI Alerts. Just first, a couple of things. It's not working. Oh, sorry. Okay. So just a couple of words about Video AI Alerts. So this is actually also presented in our last year's presentation. So if you are interested in the core algorithm design or the use cases, you can check out our last presentation at the link provided here. So basically, Video AI Alerts is an anomaly detection service for internet video streaming analytics. So what it does is, at every minute, it tries to detect anomalies in the quality of viewing experience from a huge number of potential issues and do analysis on all the anomalies to figure out the root cause. So the problem addressed by Video AI Alerts is actually very important for internet video delivery because it provides visibility to issues in the delivery pipeline and can narrow down the issue to its true root cause. And this is actually very critical to the content publishers because quality is a very important factor to viewers' engagement. So Conviva has been measuring the video quality and the viewer engagement for several years. And we have observed a consistent correlation between the quality and the viewer's engagement. So basically, just one tiny bit of change in the video quality can cause viewers to stop watching the video much earlier. So it is important to detect the quality issues and fix them as early as possible. But anomaly detection in the video industry can be a very hard technical problem. So if we take into consideration of all the complexity and the scale of the video delivery ecosystem. If we look at this diagram, this is just showing typical delivery pipeline for internet video streaming with the bare minimum components in it. So you can already see that there are many entities involved in here, and they all further form many paths to deliver just one piece of data. But there's no end-to-end owner to the entire pipeline. So any component can fail at any time randomly and can cause degradation of the video quality. So if we throw in some numbers in this delivery pipeline, so the challenge becomes even easier to see. For example, the number of video assets can go up to several thousand for any content publisher. And there can be hundreds of origin servers, tens of ISP, several CDN, and thousands of cities around the world. So basically, we are facing millions of combinations of possible issues. And it is just technically hard to do anomaly detection and root cause analysis in a timely manner with this scale. So next, I'm going to talk about the design of the AI alert system. First, several definitions. Grouping. Okay. Grouping is just defined as the entities along in the delivery pipeline. So in this example, device, ISP, CDN are the grouping, and their combinations are also valid grouping. So grouping defines where the potential issue can happen. And then sessions are just data records for the specific video session. It contains grouping metadata and the QE measurements. And the sessions can be grouped together based on their grouping metadata. For example, all the people watching video on iPhone can belong to the same group of iPhone. And their QE metrics can be aggregated to generate the group level QE metric. So the group are just defined as the aggregated QE metric from all the sessions. And the groups are actually the inputs to the AI alert system. So this diagram shows the system level architecture about the AI alert system. The small boxes at the top are the video players, and these players run the Conviva sensor in it. The Conviva sensors just constantly measure the quality of viewing experience for each specific viewing session, and periodically send those measurements to the Conviva backend, which is everything below this blue line. And then our real-time computation stack will aggregate those measurements and form the session-level summaries, which are stored in HDFS. And then that can be consumed by various applications, such as AI alerts. So video AI alerts is the system is essentially a Spark cluster. So it's based on Spark 2.0. The system periodically loads the summarized session data from the HDFS and aggregate those session data into the group level QE metrics and form the time series, and then run the anomaly detection and root cause analysis algorithm on the group level data. And then the alerts will be generated and stored in a database, and which can be consumed by the external application. So now we can dive into the details of the Spark system. So the system is essentially a Spark cluster. So it executes following a few jobs every minute. So the first job is to load sessions from the upstream HDFS. So the each executor will load a bunch of files, and the session level RDD is constructed here and cached in the cluster. And then the next job is to aggregate the session level data into the groups and generate the time series. So the session RDD is then first transformed into the group level RDD. As you can see, data shuffle is involved here because data needs to be aggregated. And then the group level RDD is then further joined with the historical data to form updated time series. So a new RDD is generated here, which is the time series RDD. And then the time series needs to be further shuffled around so that the data that belong to the same customer can be in the same partition. So this is required by the anomaly detection algorithm. And then after this time series RDD is generated, the cluster will just run the anomaly detection algorithm on each partition in parallel, and then the alerts will be generated and persisted. So all of these jobs need to run periodically. Right now, we are using a 1 minute batch, so the jobs are supposed to be done within a minute. So now let's talk about the challenges we have been facing and what we have done to overcome them. So keep in mind that all these challenges may not be real issues. So if you don't take the consideration of scale, latency, and cost, and for our application, the amount of data is huge. So basically, every minute we need to process millions of session data, which can be several gigabytes of data, and we need to finish all the job with very low latency. So the challenge is a real issue to us. So the first challenge we are facing is we are dealing a long-running Spark application with short latency requirement. So basically, we need to keep the service run for weeks with minimum performance degradation. And then we need to minimize the latency of the job so that we can deliver the alerts in a timely manner. Without pipelining, reading and processing 1 minute data has to be finished within 1 minute. And it is not easy to do pipelining in Spark. And then the second challenge is the upstream components, which is the HDFS, is not always reliable. So basically, we have seen that the size of the session data can be skewed, which can directly cause the skewed partitions of the session RDD, which further affect the performance of the downstream jobs. And then the number of session files may vary. So basically, the number of files may be smaller than the number of cores in your Spark cluster, so which causes less utilized CPU. And then the HDFS data node can fail or degrade at any time, which directly causes a long delay in loading the session data. So the third challenge we are facing is right now the cluster is running in AWS, so the EC2 nodes are just not always reliable. So we have seen the failure and the degradation of the worker nodes, and what's worse is the failure or degradation of the master and the driver. So how we can overcome all these challenges? So here's what we have done. First, we need to monitor both the Spark performance and the application health for those long-running Spark applications. And we need to make it easy to correlate these two sets of monitoring for troubleshooting. And secondly, we need to focus a lot on scalability, stability, and resilience. So a couple of techniques will be explained in details in terms of how to improve this SSR. And thirdly, we have done lots of software-level optimization for better scalability and lower cost. So specifically, we have tried to reduce the data shuffle, and we try to optimize the data serialization. So next, I will pass it to Shubo to give more detailed explanations on each of the items here.
So before we talk about the details, let's first take a look at our achievements. This is a result we done in the same staging environment. Now we are able to process 4x load with slightly less execution time, but with the same computation resource. It's achieved a high performance system with also cost efficiency. So our journey starts with understand how our system performs. It's actually a combined effort of both the individual Spark job optimization and all our software application monitors. The classic Spark job monitor helps us to optimize each individual Spark jobs. Most people do it through Spark UI, but in some cases, we could also enable a Spark event log and get more data from different stages using historical server. At this time point, we are looking for the DAG, which is the detailed logic plan for the subminute jobs. It helps understand how the job is executed and where its data shuffle introduced. We are also looking for some of the key performance data metrics, such as execution time, memory usage, input-output size. It helps us understand the bottleneck at the Spark job level. However, either Spark UI or historical server could provide very limited information. In our experience, we found even for the same Spark jobs, the performance may vary from time to time. Additionally, it's also hard to identify a system-level bottleneck through only a few iterations. So we need a tool with long data retention policy and also could help us to correlate Spark performance with application-level KPIs and sometimes even with the external business logics. There are quite a few options in the community today, such as Conviva Manager, which gives you a one-stop overview of the health for the whole big data ecosystem. Some people also use Splunk and Elasticsearch to pass in the application log and monitor application-level performance metrics. At Conviva, we are kind of combine the benefit of those two options and build our in-house tool named Hermes. The advantage of using Hermes, it is easy to integrate with different data source and also very flexible to present those data. The Hermes is designed in a client master mode, On the client side, we deploy an agent to each application host. This agent could push data from either the performance counter defined by the programmer or from the industry standard plugin, such as Sensu Nagios. Those data then sent to a server who synchronizes the result from multiple hosts. Those data then could be used to trigger a notification or feed into a customer dashboard. This is one example of the Hermes dashboard through Grafana. With this, we are able to monitor the performance, the system health over a long period of time. This is probably a few days. And also pinpoint the system hotspot, narrow down the root cause during the performance degradations. Now, let's start our sharing with the SSR project from the system perspective. So early last year when we began this project, the first challenge to us is the system faster recovery. Conviva video AI alerts is running based on a large-scale statistical model. There are around 10 million parameters in the model. It's trained from 250 million raw data session points. So these model states are distributed among the worker nodes. As every distributed machine system, single point of individual node failure is almost inevitable. So in usual cases, Spark could handle the worker node failure. RDD could be reconstructed through lineage. However, in our use case, because this model is trained based on approximately 2 hours worth of data, this recovery could be really expensive. As an alternative, we decided to materialize the RDD and persist the checkpoint. The checkpoint then could be reused by Spark framework automatically for worker node failures. I guess a lot of people is doing similar things for long-running Spark applications, especially for those in the Spark streaming applications. However, how about the master and the driver failures? As most of Spark applications, the master and driver are the 2 single point failures. So the master driver failure requires a service restart, and also the model state need to be retrieved. We refer this period as a warm-up. So the warm-up could be done using retrain the model using the historical raw data, or we will have to wait until a new model is available. In our use case, considering the scale of our model, each option takes approximately 2 hours. Unfortunately, we have to pay this warm-up cost every time we restart the service, either due to the code deployment or because the disaster recovers. It has a huge, significant negative impact on our system SLA. So how we could do about it? Well, as a distributed statistical model, most of the states are stored in a RDD, which we already have checkpoint anyway for the worker node failures. So when the driver or the master dies, the Spark context gets destroyed, and we lost these metadata. But the actual checkpoint data is still in the HDFS. Spark won't delete it for you. So we thought, why not we recycle this data for the new application warm-up. So that's what we ended to do. When we checkpoint the RDD, together with it, we also persist the checkpoint metadata into HDFS. This is minor extra cost at real time. It's probably a few kilobytes per iteration, but it actually brings us a huge benefit later on. When we restart the service, we create a new the Spark context, but rather than retrain the model, we use the checkpoint files to recover it. As long as the key data structure and the Spark conversion is compatible, this RDD could be used to detect the anomaly directly. With this system, we actually now could be able to recover our system in approximately less than 2 minutes compared to 2 hours before. That's bring us a huge benefit. So the next obstacle to us is the upstream. When the data upstream is not on your payroll, it usually poses challenges to your scalabilities. In these slides, I would like to share 2 great tools with the audience today. The first tool is the Hadoop file split API. The Hadoop file split API allows you to split the original partitions into smaller chunks so that we could have more executors to work in parallel. Additionally, we could control and optimize the request file numbers so that every worker has approximately the same amount of data to process. Second thing is the Spark test speculation. So occasionally we observe that the raw session loading stage takes longer than normal. It takes up to 80 seconds compared to a normal state, probably 20 seconds. Thanks to the Hermes, we identified that the root cause is because we are competing I/O with some of the other applications on better performance data nodes. So in this situation, Spark test speculation helps. It basically relaunch a duplicate task after it observe a long-running abnormal task, and then the master could collect the result from the first completed one and then moves on. It helps to accelerate the overall Spark job, especially for those involving external data transfers. Now today we move our cluster size grows and grows, so we are moving our application to the cloud. As we know that the cloud host is not as reliable as our in-house machines, so there's a demand for the high availability designs. The main use case here is for the driver and master fail automatic detection and restart, because the worker failure is, we discussed, it could be handled by Spark framework and through checkpoints. So the Zookeeper and the Yang and the common choices for this kind of use case. But I would like to share the audience today is that if you want to use Yang to handle the driver failover, you must prepare each worker to become a driver in the future. If this preparing requires some service that could not be manageable by Yang, it's actually more convenient to build your own Zookeeper and handle the driver. That's turned out to be what we did in the video AI alerts. Now, this wraps up our sharing from the system perspective. Now I would like to take some time and talk about the software level optimizations. At the end, in the previous slides, we shuffle data a lot. So the general principle for us is try to reduce the data shuffle as much as possible. So I suggest everyone begin to use the Spark deck to audit your job, because you may be able to find some unexpected unnecessary data shuffles. Let's take a simple code examples here. So the examples here start with a simple word count. And then we do some transformation to this word count RDD and join those two RDDs together. In this example, I simply multiply the value by 2, but in a real scenario, we actually use slim operation to form a time series. This job could be done in approximately 77 milliseconds and 5 kilobytes data get shuffled, because our original file is quite small. But when we look at the deck, there are actually 2 shuffle stages. It's kind of a surprise to me because that we don't touch the key in the second map operation, why there's additional shuffles here. It turns out that the map operation itself will erase the partition information in the original word count RDD. That's the reason we have these additional shuffles. So as an alternative, we could use the map values to achieve the same logical result, but with a lot of significantly reduce the execution time and shuffle data. Double check the deck, it looks reasonable because the one shuffle stage, it looks reasonable. In some other cases, if your transformation requires the key in the operation as well, we could use the map partitions to preserve the partition information as well. That's what we did in the video AI alerts. We successfully reduced the 2 shuffle stages, and we also reduced 20% with respect to the execution time. So in the previous slides, we talked about the checkpoint is very important to our system. It's useful, but also very expensive. We checkpoint around 2.2 gigabytes data into HDFS each iteration. So I think it's time for us to considering optimization for serializations. The general strategy here is we trade extra computation resource for less I/O. Specifically, we removed those derived fields and also write own customer CRD. Let's also take a simple examples. So here we have 3 versions of a log object class. So there's an inventory field record the number of goods in our warehouse every day. And also we have a start date, end date, and a size to this log class. Because the size could be easily computed through using the difference between end date and start date. So we remove it at a real time. Let's take a further down, we write our own customer CRD. The key point here is we avoid using the Java Scala object int double, but use the Java primitive type as a replacement. Additionally, we also use the array rather than sequence in this 3D. It turns out that each operation gives us some benefit, especially after we write our own customer 3D. The same 100,000 objects could only use 23% of original storage space. That's also help us to reduce our checkpoint files in the real production scenario. Now our checkpoint files is only around 1.5 gigabytes. It's around 35% reductions. The same thing helps us to reduce the data shuffle as well. A lot of people, actually, some people are using Cryo as their out-of-box solutions for the 3D, but in our experience, actually, Cryo is not that easy to use. If you have a lot of class to load by Spark, but only a few of them need to be persisted and optimized, it's actually more convenient to write your own 3D rather than fix a lot of bugs in Cryo. That's just our experience. So let's summarize what we talked today. So we talk about optimize the data ingestion to achieve higher parallelism and lower the session loading variance. We talk about the Spark optimization by reduce shuffling. We also talk about using the checkpoint for the system faster recoveries. To enhance that, we also write our own 3D for less I/O. So today, compared to the Spark Summit 2017, Conviva's video AI alert is now scaled up by 7 times with respect to load, but with only 2.5 times computation resource. We also achieve a high SLA as well. So our journey posted here. Of course, there are more challenges for us in the future, such as advanced algorithms, scalable system, and a higher standard for SLA. So that's why we are hoping like more talents could join us in this exciting adventure. Now we have a few minutes, we could answer some questions. Thank you.
There are microphones in the middle of each aisle. If you want to come ask some questions, we have 3 minutes.
You said you do the checkpointing. So how do you optimize your checkpointing if the file size grows, let's say TBs or many more GBs?
Yes, so in our checkpoint files, the data is actually quite consistent. It's the same kind of class. So that's why for our class, as I shared in the 3D part, we actually carefully optimize the 3D. You write our own 3D function to reduce the size. That's kind of the thing we did for the checkpoint.
All right, let's give our speakers a big hand.